Check. Hello, everyone. Welcome to our next session. We have two presentations in this session. Both are from the research track. The track is called Robust Recommender Systems. And my name is Kaiqiao, and I'll be the session chair. The first presentation is about a reinforcement prediction allocation framework for cache allocation in large-scale recommender systems. The speaker is Xiaoshuang.
Hello, everyone. I'm Shuo from Kuaishou Technology, China. I appreciate the opportunity to share our work with you. I'm here to talk about the RPAF, a reinforcement prediction allocation framework for cache allocation in large-scale recommender systems. My presentation have 5 parts. First, I will provide a brief introduction to the background of the problems and method. Next, I will introduce our reinforcement prediction allocation framework. After that, I will demonstrate the effectiveness through experiment. Kuaishou is a short video recommendation platform. In our primary business scenario, users view one video at a time, and users can engage in various interactive behaviors, such as like, comment, and share. We are part of the recommendation team, focused on enhancing users' long-term experience with our app. To achieve better results, we implement reinforcement learning models in our online system. Here is the background. As a short video platform, we experience significant fluctuations in QPIs throughout the day. During peak periods, real-time computation requires substantial computational resources, while these resources often remain idle during off-peak times, which is not cost-effective. To address it, many large-scale industrial recommender systems use a result cache to balance computational demands and recommendation performance. When users first open our app, we provide them with a standard real-time recommendation response, which consists of key ordered items. Then store the top remaining items in a cache, usually around 4 to 5 times the size of K. Next time a user returns to the app, we have the option to either provide a real-time recommendation response or to serve the recommendation directly from the cache. In the past, we used a random strategy to decide the option, and now we are using a reinforcement learning model. Cache results are suboptimal compared to those generated through real-time computations. In the second graph, the watch time of request decreases when users continuously receive cache recommendations. This indicates that cache recommendations are not only affects the current request, but also has long-term impacts on users. In our approach, reinforcement learning consists of samples and models multiple requests from one user. However, this model must satisfy the global constraints, specifically the computational resources limitations for all users. This problem has 2 main challenges. First is how to model the long-term value of user requests while satisfying global traffic constraints. Second is related to the streaming allocation. Online recommendation systems receive requests in a streaming manner, which requires the system to make cache decisions for each incoming request. This is our architecture, which consists of a 2-stage framework. Sorry, because this is not very useful. Okay. You can see different optimization objectives of critical and actor. Our binary action refers to 2 possible behaviors. Regarding the user's current request, either receive real-time recommendation or cache recommendation. In the lower part, during the model inference, we need to solve the following constraint optimization problem. In the RPAF framework, we use a modeling approach named RLA. Here are some proofs to it. During the prediction stage, we relax the action. We relax the action and transforming it into a continuous value that reflects the probability of whether a user's request should be a real-time recommendation. By replacing it, we can rewrite the actor as the final equation. The training process must consider the constraints of the global computational resources. Here, x height represents the estimated computational resources currently in use, while x denotes the total available computational resources, which is related to the number of active machines and can be regarded as a fixed value. The penalty function t needs to satisfy two conditions. It should reach its minimum value when x height equals to x, and t should be convex with respect to x height. We can choose the penalty function in these two forms, mean squared error and the KL divergence. By using the chosen penalty function into the actor's training formula, we have following equation. By minimizing it, we can obtain the policy that maximizes the critic function Q under the budget constraint. We compare several methods in our offline experiments. The performance metric we use is average watch time. The results shows the significant improvement. To further validate it, we tested this method in Kuaishou, an online short video platform with over 100 million users. We use the number of daily active users as our evaluation metric. Finally, if you are interested in the application of reinforcement learning in recommendation systems, please don't hesitate to contact us. That's all. Thanks for your time.
Let's thank the speaker.